What are linear systems? A linear system is one whose behavior is predictable and consistent over time. A time-invariant system reacts the same way no matter when a signal is applied. If we shift the input in time, the output shifts the same way. It's called linear because it obeys the superposition principle. If two inputs are applied, the same total response is just the sum of each response scaled appropriately. Engineers describe these systems using linear differential equations with constant coefficients, which makes the analysis much simpler. Finally, the system's outputs can be calculated by convolving the input with its impulse response, a cornerstone idea in signal processing and control theory. Linearization and transfer functions. Real machines and physical processes are often nonlinear, but around a steady operating point, their behavior can be approximated by a linear model. This process is called linearization, and it yields a transfer function or a state space model that relates inputs to outputs through linear differential equations. These models allow us to analyze stability, frequency response, and transient behavior using tools like bold plots and linguistic diagrams, and to design controllers such as PID or state feedback controllers. By reducing complex dynamics to an LTI form, we gain insight and predictable performance. Linear equations are the foundation of aviation systems. Autopilots use them to keep the aircraft steady, while control surfaces adjust flight paths through the linear feedback. Inertial navigation and radar use linear math to estimate position and detect signals. Even anti-lock brakes rely on linear control to prevent wheel lock and keep the plane safe during landing. In aviation, autopilots provide a classic example of negative feedback control. Sensors such as gyroscopes, accelerometers, GPS, and airspeed indicators measure the aircraft's state and feed data to a computer. The computer commands servo motors to adjust control surfaces. Simple single-axis autopilots correct roll by moving the ailerons. Two-axis systems add elevator control for pitch, and three-axis systems include the rudder for yaw. Servo motors act as the aircraft's muscles, converting electrical commands into mechanical motion. By linearizing the aircraft dynamics around the trim condition, engineers design autopilot gains that maintain stability and provide smoother flight than a human pilot can achieve, extending even the auto land system that flies an aircraft down to the runway in poor visibility. Radar systems illustrate linear filtering on a different frontier. When a radar transmits a pulse, the echo received from a target is convolution of the transmitted waveform with the target's response. Match filters correlate the received signal with a time-reverse copy of the transmitted pulse and are proven to maximize the signal-to-noise ratio. In practice, radars employ banks of match filters or pulse compression techniques to cope the Doppler shifts caused by target motion and to improve range resolution. Designing and analyzing these filters relies on the linear system perspective, treating convolution and the Fourier transforms as fundamental operations. A self-contained inertial navigational system uses three orthogonal accelerometers and three orthogonal gyroscopes to measure linear acceleration and angular velocity. Integrating these signals yields estimates of velocity, orientation, and position, but sensor biases and noise cause errors to accumulate over time. A Kalman filter combines a mathematical model of the vehicle's motion with noise sensor measurements to produce an optimal state estimate with minimal variance. Widely applied in aircraft, spacecraft, and mobile robots, the Kalman filter exemplifies linear estimation. It assumes the underlying dynamics are linear and updates the state estimate recursively as new data arrive. While at sea, autopilots perform a similar job. A typical marine system comprises a controller, a heading sensor, a computer, and a rudder sensor. The fluxgate compass wraps coils of wire around a ferrite core. When Earth's magnetic field cuts through the coils, it induces a voltage that indicates heading. Advanced systems integrate GPS, wind vanes, vertical angle sensors, and gyros to hold a course and optimize fuel consumption. Like aircraft autopilots, marine autopilots tune feedback gains so that the vessel tracks the desired heading without oscillation, an application of linear feedback control in a hydrodynamic environment. In automobiles, cruise control maintains a steady speed by continuously comparing the actual speed measured by the speedometer to the driver's set point. If the vehicle is slower than the desired speed, the controller opens the throttle. If it's faster, it reduces the throttle. Properly designed cruise control uses proportional integral control to keep the speed near the set point despite hills or wind. Modern adaptive cruise control adds radar sensors to maintain safe following distances. Again, the car's longitudinal dynamics are approximated by the first order LTI system, allowing engineers to design gains using linear system theory. An anti-lock braking system prevents the wheels from locking during a hard braking by sensing each wheel's angular velocity and modulating hydraulic brake pressure accordingly. The controller rapidly reduces brake force when a wheel nears lockup, then reapplies it to maintain traction and allows steering control. This cycle repeats many times per second. Although tire-road interaction is nonlinear, designers approximate the wheel slip dynamics by linear models within the operational range and implement feedback controllers to achieve robust stopping performance.
Video game consoles. When it comes to video games and their consoles, filters are utilized prevalently. The filters used in video games follow an LTI system behavior. These LTIs work by having a set impulse response and using that to transform the input. It works by having an input, passing it through an LTI system, and that LTI system will transform it and give you the output. Audio experiences modification through equalization, noise reduction, and echo reverb. Graphic experiences modification through sharpening, blurring, and edge detection. The way audio can be processed in video games is by using something known as a digital filter, which takes in the audio from the game, modifies it in real time, and affects how the audio is heard by the person playing the game. These digital filters rely on the principles of LTIs, which means its predictable behavior, which is defined by its impulse response. The input goes through convolutions using the system impulse response, resulting in the output audio. Forms of audio modification include equalization, which adjusts the gain, like an op amp seen in circuits, except this actually uses multiple frequencies, not just one. It can also be modified using reverb, which delays the copy of the original audio to produce the desired spatial effect, such as in caves where you hear echoes, it can produce that sort of effect. Another form of modification is noise reduction, which reduces unwanted background noise while preserving voices and music. LTIs are also seen when rendering graphics for video games. An example of this is convolution kernels because they use the same methods and the same principles as LTIs for transformations. It is seen when you have an input pixel A that passes through a specific kernel, which is a matrix, and it then transforms it into pixel B. No matter where in the image the specific kernel is placed, it will always produce the same output effect on said pixel. Examples of such predictable transformation include sharpening, blurring, color changing, resizing of an image, and edge detection. It is thanks to these kernels that developers of video games or any graphic media have full control over how an image output will look like. When it comes to video game consoles, the visuals, the audios, that's not the only thing using linear systems. You can also look at the hardware itself. The thermal control would be a big example. When it comes to controlling a hardware's temperature, nested negative feedback loops are utilized in order to approximate nonlinear data using linear operations. PI controllers allow us to estimate the fan speed, temperature, and heat dissipation in linear systems as opposed to using nonlinear systems. These PI controllers take an input and compare it to the desired output. It then calculates what needs to be done to reach to that desired output. An example could be that a CPU is at 70 Celsius and the desired Celsius is actually 50 Celsius. That means that there's an error of 20 Celsius when you take the difference between the two. The PI controller does that math and then it calculates what it should do with the fans. It should speed it up, maybe 70%, maybe 80%, but it will do a specific calculation to figure out how it can reduce that error from a 20 Celsius error to a 0 Celsius error. Everyday appliances can also use linear systems. When it comes to everyday appliances, things such as home sensors and headphones, they utilize filters to provide the best experience. These appliances, although different, follow a type of LTI concept. Smart home appliances can use calm filters, while noise-canceling headphones utilize linear filters. Smart home sensor filters. These sensors are pretty good at picking up signals, but they may also pick up unwanted noisy signal that messes up the important signals. That's where common filters come in handy, reducing the impact of these unwanted noise the sensors may pick up through the use of predictions. These common filters work by using previous values and compare it to the new one. Common filters can predict which data is more reliable based on how things should actually work. It prioritizes the more reliable data and gets a balance between the two. If it were an IDHS that utilizes temperature sensors that process using common filters, the temperature should not spike rapidly in a very short time. In that case, it would prioritize the previous data, but it would get a balance between the two, the normal data and the spiked one, but prioritizing the normal one, of course. Finally, we have active noise cancellation. Headphones that have capabilities of canceling out noise from the outside does it with something known as a destructive interference. The use of LTI theory can be used for this where the input is the noise, then an FIR is used to generate a specific noise. That would be a destructive interference that can then be used to cancel out the input noise. This causes a noise cancelling effect through the use of superposition principles because we're taking an opposite frequency with the frequency of the sound, you put them together at the same time, and it cancels it out.